So get this. The year is 1905, and a 26-year-old patent clerk publishes a paper. And this paper is about to completely detonate everything we thought we knew about space and time. It didn't have some flashy, exciting title. It was called On the Electrodynamics of Moving Bodies. But the ideas inside, absolutely explosive. Today, we're going to walk through the brilliant, step-by-step logic of that very paper. Okay, let's dive right in. To get us started, Einstein asks a question that sounds, well, almost childishly simple. What is time, really? We all think we know, right? It's just what our clocks measure. But as he points out, that's only half the story. If we really want to understand the universe, we have to get much pickier about what the word now actually means. You see, for any single spot, defining time is pretty easy. As Einstein puts it, we can just look at the position of the small hand of my watch. Simple enough. But the real problem starts when you try to connect events that are happening in different places. I mean, how can you be sure that an event happening on Mars and an event happening right here on Earth are taking place at the exact same moment? So to solve this, Einstein comes up with this beautifully practical procedure. Imagine you've got two clocks, we'll call them A and B, separated by some distance. You shoot a beam of light from A to B. It hits B, reflects, and comes all the way back to A. Now, here's the key. In that last step, the clocks are only considered synchronized if we define the time it took light to get from A to B as being exactly equal to the time it took to get from B back to A. And this is a crucial point. Simultaneity, two things happening at the same time, isn't something we just discover out in the wild. It's something we have to define. We're basically building our entire system of time on this one fundamental assumption about how light behaves. And this definition, it's the bedrock for everything that's about to follow. Okay, so with time properly defined, Einstein lays out two postulates. Think of these as the unbreakable rules of the game for his new reality. Everything else we're about to talk about is just a logical consequence of accepting these two simple ideas. The first rule is called the principle of relativity. Now, that sounds complicated, but in simple terms, all it means is this. The laws of physics are the same for everyone, moving at a constant velocity. There's no special privileged spot in the universe that's truly at rest. So the physics experiments you do on a smoothly moving train will give you the exact same results as they do on the station platform. Now, rule number 2, this one is the real showstopper. It's the one that kind of breaks your brain. It says the speed of light in a vacuum is always the same, no matter what. It doesn't matter if you're rushing towards the light source or away from it. It doesn't matter if the flashlight is on a rocket or just standing still. You will always measure its light moving at the exact same speed, c. Yeah, I know. It's completely counterintuitive, but it is the absolute key. So right away, you can see we have a massive conflict on our hands. Our everyday experience tells us that speeds add up. You know, if you throw a ball forward on a moving train, its speed relative to the ground is the ball's speed plus the train's speed. But Einstein's second rule says, nope, not for light. Something's got to give. And as we're about to see, the things that have to give are our most deeply held beliefs about absolute space and absolute time. Let's see how accepting these two rules leads to the first really shocking consequence. The whole idea of a universal now, a moment that everyone in the universe can agree on, well, it completely shatters. So here's the thought experiment straight from the paper. I want you to picture a long rod just flying through space. On its front end, there's a clock. On its back end, there's another clock. And these two clocks have been perfectly synchronized. The big question is, how do different people check if those clocks are really in sync? And here's where it gets weird. To an observer who is moving right along with the rod, those clocks will actually appear to be out of sync. Wait, what? Why? Well, because from their point of view, they have to account for the fact that a light signal sent from the middle has to travel different apparent distances to reach the front and back ends. This messes up their whole definition of synchronization. But what about for someone standing still on a platform, just watching this rod fly by? They do their own check, using their own measurements and their own definition of simultaneity. And you know what they find? To them, those same two clocks are perfectly synchronized. So, who's right? The person on the rod or the person on the platform? The mind-bending answer is they both are. And that leads to this radical conclusion. In Einstein's own words, we can't attach any absolute signification to the concept of simultaneity. It means that two events that happen at the exact same time for one person might not happen at the same time for another person who's in motion. The idea of a universal now is, well, it's just an illusion. And this isn't just some philosophical mind game. This new, strange reality has real, physical, measurable consequences for actual objects and actual clocks. Let's talk about slowing clocks and shrinking rods. Okay, first up, length contraction. Think about it. To measure the length of a moving object, you have to know where its two ends are at the same time. But we just proved that at the same time is relative. So it follows that length itself must also be relative. An object in motion is literally measured to be shorter in its direction of travel. Einstein gives us a really powerful visual for this. Imagine a body that's a perfect sphere when it's sitting still. Well, if you see that same sphere in motion, flying past you, it will appear squashed into an ellipsoid. It doesn't feel squashed to itself, of course, but to a stationary observer, it absolutely is. The second consequence is just as strange, maybe even stranger: time dilation. Not only do moving rulers shrink, moving clocks run slow. That's right. From your perspective, a clock flying past you at high speed will literally tick more slowly than the one on your wrist. And this leads directly to one of the most famous ideas in all of physics, the so-called twin paradox. If you take one of two perfectly synchronized clocks, send it on a long, fast journey, and then bring it back, it will have recorded less time than the clock that stayed put. The traveling clock literally ages less. Wild. Now, all of this, shrinking lengths, slowing time, it all points to one ultimate, final conclusion. The universe has a speed limit, a cosmic speed limit, and it's enforced by the laws of energy. Because space and time themselves are warped by motion, the old simple rules of just adding velocities together no longer apply. The new formula that Einstein derives shows that no matter how many times you push an object, no matter how many boosts you give it, you can get it closer and closer to the speed of light, but you can never, ever quite reach it. So the speed of light, c, it isn't just another number, another velocity. It emerges from the math as a fundamental property of space-time itself. It's an absolute barrier. It is the ultimate speed limit in our cosmos. And, as we're about to see, nothing with mass can ever hit it. And here's the reason why. The paper shows that as an object's velocity gets closer and closer to the speed of light, its kinetic energy, that's the energy of its motion, it approaches infinity. So to actually reach speed c, you would need an infinite amount of energy. And, well, that's just impossible.
And what's just so incredible about all this is that this new framework for space and time wasn't just some wild speculation. It beautifully solved real, nagging inconsistencies that existed in the physics of electricity and magnetism. It actually revealed that electric and magnetic fields are fundamentally the same thing, just viewed from different frames of reference.
Which leaves us with a final, really profound thought to chew on. Einstein took the things we all thought were fixed, the things that were absolute, like space and time, and he showed they were deeply relative. So if our most basic, fundamental intuitions about how the universe works can be so completely overturned, what's left? What is truly constant that we can anchor our reality to?